All right, folks, we're back and better than ever working on section 11.7, the polar form of complex numbers. This is part 2, and in part 2, we're going to be doing 4 things. We're going to be looking at products, quotients. Remember, product is multiplication, quotient is division. And then on page 2, we're going to be looking at exponents and roots. And that's it. There's just 4 things, so we're going to go through these examples pretty quickly. And this chapter is called, chapter 11 is called Applications of Trigonometry. And I'm going to be honest with you, the stuff I'm doing here, the product rule for polar form of complex numbers, quotient rule, power rule, and roots, that's pretty deep in the weeds. I can't say that this is going to be something I think you're going to apply a lot in your future mathematical career, but we're going to persevere through it anyway and see if we can learn a little bit of extra trig along the way. So before I get started with looking at a couple of these product rule examples, I want to remind you that we're going to be working from the following with the following parameters. If z and w are complex numbers with polar forms of z equals the modulus of z times c plus I sine alpha. Okay, so alpha will be the angle for z, and then we have a similar relationship here with w, where we have the complex number in polar form of w equals the modulus of w times cis of beta. Then these two rules hold, but let's just go back to this for 1 second. In the previous video, I talked about what this means. This means that z equals the modulus, which can be thought of as the radius of the complex number if it were in polar form. So we have the modulus or the radius times the following. Cosine, forgot the c. Holy cow, you deserve better, folks. Let's start that over. We have cosine of theta. So modulus of z times cosine theta, that's the real component of this complex number, plus I times sine of theta, and that is the imaginary component. So if we distribute the modulus, z times cosine theta, that's the real piece, and the modulus of z times I sine theta, that's the imaginary piece. And that gives us a complex number, real plus imaginary. Okay, so let's move on. Let's do an example. First thing up, for the following pairs of polar numbers, compute the product z times w, express the answer in polar form. So here's my number z, here's my number w. If I look up here at the product form, I know I need the modulus of each. I also need the angle for each. So I'm going to go ahead and do both of those things now. The modulus of z is going to be equal to 5 root 2 squared plus negative 5 root 2 squared, and then I have to take the square root of that whole thing. Now it's written there in kind of a strange form. It says 5 root 2 minus 5I root 2. Remember, this is multiplication here. It does not matter what the order is. It still gives us the same product. So we go ahead and compute this. 5 times root 2 squared, that's going to be 50. Negative 5 times root 2 squared, that's also going to be 50. So the modulus of z is 50 plus 50. Square root of that, square root of 100 is 10. Let's go ahead and take a look at the angle for this complex number z. It's got a positive real component, a negative imaginary component. That's going to put it down in quadrant number 4. Alright, so we're going to have an angle about here. I noticed that both the real and imaginary components have the same magnitude, that 5 root 2 number. So that's pretty easy for us to figure out what the angle is going to be. So this piece here is 5 root 2. This piece here is 5 root 2. And here's the angle, which we're calling alpha. And if I'm down in quadrant number 4 and my x and y coordinates have the same magnitude, that means alpha equals negative pi over 4. All right, so why did I pick negative pi over 4? If you recall, yesterday we talked about the principal argument of the complex number in polar form would go from negative pi to positive pi. All right, so that's all the pieces parts we need for z. Let's take a look at w. For w, we'll do the modulus first. That's going to be 5 root 3 over 2 quantity squared plus 5 halves quantity squared, and then we're going to take the square root of that whole thing. So 5 squared is 25 times 3, it's 75 plus 25. We're going to have 75 plus 25 all over 4. Got to take the square root. Let's see, that's going to be 100 divided by 4. That's 25, so the modulus of w is going to be the square root of 25, which is 5. All right, now in terms of the angle beta for this complex number w, it's got a real component in quadrant 1 and an imaginary component, a real component positive, imaginary component that's positive. That puts us in quadrant 1. So we'll go ahead and sketch out the angle here. And this is the angle beta. So the x component is 5 root 3 over 2. The y component is 5 halves. And let's see that. So I'm going to let's figure out what that is. Beta is going to be equal to the inverse tangent of the y component divided by the x component, imaginary divided by real. So if I take 5 halves and I divide it by 5 root 3 over 2, that's going to give me 1 over root 3. Anytime I have a tangent ratio with the root 3 in the denominator, I know that's one of my angles on the unit circle whose cosine is root 3 over 2. That happens at pi over 6. So folks, we have all the components we need to do our calculation. Those components are the modulus of z, the principal argument of z, the modulus of w, and then the principal argument of w. So let's go to our formula. Our formula for the product of z and w is the modulus of z times the modulus of w, and then times CIS of alpha plus beta. So let's go ahead and substitute in what we know. Modulus of z is 10. Modulus of w is 5. And then alpha is negative pi over 4. And beta is pi over 6. Okay, so right at this point I want to highlight something here. I'm adding these two angles. If you recall, CIS stands for cosine theta plus I sine theta. We don't actually have to find the cosine of the sum of these two numbers or the sine of the sum of these two numbers. All we have to do is add them. If I did ask you to find the cosine of this sum, then you'd have to use our sum difference formula for cosine. Same if I actually asked you to find the sine of that number. But I'm not asking you to do that. I'm just asking you to represent the complex product in polar form. So this is going to be 50 times CIS. Okay, so now I got to add something with a denominator of 4 and something with a denominator of 6. So I'm going to multiply negative pi over 4 times 3 over 3. That's going to give me negative 3 pi over 12. And then for 6, I have to multiply 2 over 2 to get 12. It's going to be 2 pi over 12. Now I think we can write out our final answer. The product z and w is equal to 50 CIS of negative pi over 12. And that's your final answer. I'm going to go ahead and grip it and rip it through the next one. Let's pause the video and see if you can do it before I do. Wow, folks, that was a lot of work for one answer that's just really not all that appealing, is it? We came up with 9 CIS of pi over 12, and that's it. One thing I'd like to comment on here, in my notes, I'm going to post a solution that I used a little different approach. Instead of calling alpha negative 2 pi over 3, I called it 4 pi over 3, which doesn't make it the principal argument because it's bigger than pi, but it's still an argument of the complex number z. The problem with that is when I added the angles in here, I ended up getting something that was too big to be a principal argument, and I had to reduce it. But the final answer is still the same. This approach is actually a little more efficient. Okay, so let's move on to example 2 here. Example 2, it says for the following pairs of polar numbers, compute the quotient z divided by w, express the answer in polar form. Let's come up here and take a look at what the form is for the quotient. Okay, so the quotient of z divided by w is just the modulus of z over modulus of w times CIS. So far things seem to look pretty similar to what we've been doing, but this time it's going to be alpha minus beta inside the parentheses. So everything we're going to do here is going to be the same as the procedure from above in terms of finding the modulus and the angle for each complex number. If you look carefully, though, the examples here that I gave you, they're the exact same examples as the previous problem. So in question 1a, we have 5 root 2 minus 5i root 2. That's the same darn thing down here in example 2a. So I've saved you a little bit of time here because you already know the modulus and the angle from the previous example. So I'm going to go ahead and just rip through these examples real quick. At this point, it's basically plug and chug. We're taking things we've already calculated and plugging them into a formula that's at the top of the paper. Okay, so I'm almost done with this problem. Take a look at where we're at. We do have one tiny little issue here before we can call this answer final. Negative 17 pi over 12 is not the principal argument. Okay, it's not on the interval from negative pi to pi. So what we have to do is we have to adjust this thing. We have to add 2 pi to it so that it gets us back on the interval from 0 to 2 pi. So let's take a look over here. If I take negative 17 pi over 12 and I add 2 pi to it, that's like adding 24 pi over 12. And that's going to give me, let's see, we're going to have 3 that's going to give me 7 pi over 12. And that is on the interval from negative pi to pi. So we can go ahead and call that our final answer. We're going to have the quotient of z and w equals CIS times CIS of 7 pi over 12. And now that's our final answer. Okay, folks, I'm going to shut it down and finish off side 2 in another video.